Dear friends, everybody is familiar with coffee. It is one inseparable companion of our daily life. And to do coffee, we need machines. We take for granted that they are there and that they work. And nobody takes care how. In this presentation, we want to discover the magic of one of those machines. This is one of the simplest and most ancient ones, very popular in Italy and South Europe. It is called the moka pot. It was invented by Alfonso Bialetti in 1933, and since then more than 300 million pieces have been sold worldwide. Let's see together.
The video starts describing briefly the machine and its process. Soon after we show two experiments where we get important data from. Then we attempt a description from a scientific approach using thermodynamics. The data from the experiments need to confirm the correctness of the simulation. At the end of the presentation, we show the reasons why the model and the theory deviate. We want to understand how the moka pot works first, which are the parts and geometry, the receipt, the operation, and we display some assumptions. The parts of the moka pot are the bottom reservoir filled with water, the coffee funnel filled with coffee powder, the filter with gasket, the nozzle where the coffee gets out, and the upper reservoir where the coffee is collected for being served. The receipt consists of filling the bottom reservoir with water, put coffee, heat the pot, and stop heating when the upper reservoir is full. We hear the typical bubbling noise.
What about the operation? The water gets hot, the vapor and the air pressure push the water downwards till when it raises into the funnel. The hot water raises and encounters the coffee powder. The water with the melted coffee raises again while the filter removes the grains. The coffee leaves the nozzle and drops in the upper reservoir. What are the assumptions? The water, the vapor and the air in the bottom reservoir have always the same temperature. There are no temperature gradients. The coffee grains remain all in the funnel because the filter blocks them. Some air is initially trapped inside the coffee grains. We will see later how to simulate this condition. At the end of the cycle, all the water leaves the bottom reservoir. We start now with experiment number 1. What are the data input? The water mass is 300 gram, the starting temperature is 20 degrees, the ambient pressure 100 kilopascal, that corresponds of 1 bar absolute, and the experiment's data output are the water mass after 12 minutes, we find 198 grams, and our task is to determine the net power of the cooking plate. This is the graphic of the temperature of the water measured by a thermocouple during the heating time. The evaporated mass, capital M, is 300 minus 198, 102 grams. The enthalpy of the water at the start is 0, 300 kilogram times 84, that is 25.2 kilojoule, while 84 the specific enthalpy of the water at 20 degrees. Then the enthalpy of the water at the end is 0.198 kilogram times 417.4 equals 82.7 kilojoule, while 417.4 is the specific enthalpy of the water at boiling condition. The evaporation enthalpy, delta H, is equivalent to evaporated mass times the evaporation enthalpy, 272.8 kilojoule. The total enthalpy is delta H plus H2 minus H1, 330.3 kilojoule. The cooker net power is therefore this amount divided by the time, we find 0.46 kilowatt. In this way, we neglect all the losses, because we have metered the power needed to heat the water only. Now we start the experiment number 2. The moka pot dimensions are: bottom reservoir without the funnel 325 cubic centimeter. The coffee volume is 100 cubic centimeter. The total volume for water plus air is bottom reservoir without the funnel plus half of the volume of the coffee, because we assume the coffee grains do not occupy the total space. There is some room also for the air. Of course, this is our assumption. The experiment data input are the water mass that we meter, 303 grams, the coffee powder that also we meter, 30 grams, the starting temperature 22 degrees, the ambient pressure that is 1 bar absolute. The experiment data output that we are looking for are the coffee start temperature Tb, the coffee end temperature Tc, the coffee liquid mass, and the cooking time. What are our tools? We have the Bialetti moka pot 100 cubic centimeter. This dimension refers to the volume of the coffee. Then a thermocouple Astro AI, and the induction cooking plate with an adapter, because the Bialetti moka pot is made of aluminum. As we have seen in the previous slide, we had made a sort of hole in the coffee moka pot filter and in the funnel to insert the thermocouple to touch the water inside the bottom reservoir. The coffee starts at 99 degrees. The coffee ends at 126 degrees. The liquid coffee mass in the upper reservoir is 272 grams, and the coffee liquid mass in the funnel is the total mass 49 minus the original mass 30, 19 grams. The cooking time is 5 minutes and 5 seconds. Which model we adopt for the simulation? The thermodynamic fluid is actually a mixture of saturated steam, water plus vapor, and air. The first transformation from A to B is isochoric. The volume does not change. The second transformation is isobaric from B to C. The volume changes. The third transformation is isenthalpic CD. The volume also changes. Actually, the transformations 2 and 3 are happening together, but we split for making our simulation simpler. Which type of fluids are we considering? For the air, a perfect gas. For the steam, a real gas in the saturation region. The volume VA as displayed is the lower volume, 375 cubic centimeters, and delta volume is the volume of the coffee which is produced when cooking. We want to determine now all the parameters of the state A. The temperature is 22 degrees, the pressure 1 bar. For the fluid 2, for the steam, we can calculate the partial pressure because it's only function of the temperature, 0.03 bar. Then we can calculate the specific volume of the water and the specific volume of the vapor, because they are also function of the temperature only. From the data input, we know the mass of the water and the total volume. We can now calculate the volume of the water and the volume of the vapor as difference between the total volume and the volume of the water. The mass of the vapor is the ratio between the volume of the vapor and its specific volume, calculated here above, and the total mass of the fluid 2 of the steam is the mass of the water plus the mass of the vapor, but substantially does not change with respect to the mass of the water.
The total volume of the steam is the ratio between the mass of the steam and its volume. We find this amount. And also the steam quality, which is very important, as ratio of the mass of the vapor and the total mass, 4.58 into 10 to minus 6. This is dimensionless. The other variables are the internal energy, which is only function of temperature and steam quality, as well as the specific enthalpy that we can calculate. For the fluid 1, air, the pressure is the difference between the total pressure and the pressure of the steam. We find 0.97 bar absolute. The total volume is the same volume of the vapor because they share the same space, and with the state equation we can determine its mass because we know all the other parameters, the pressure, the volume and the temperature. The other variables for the air, the internal energy and the enthalpy, are only function of the temperature by means of the coefficients Cv and Cp that we know. Finally, we can find for the fluid mixture the total enthalpy as sum product of the masses and the specific enthalpies. We find 28 kJ. We'll assume all the findings in the table aside. In blue we have the properties for the air, in red the properties for the steam, and in black the properties for the mixture. What about the state B? We remember that this transformation is isochoric. The temperature of the state B we have measured by means of the experiment, 99 degrees, and the volume stays the same, 375 cubic centimeter. For the steam, the pressure is a function of the temperature only. We find 0.98 bar, as well as we can calculate the specific volume of the water and the specific volume of the vapor. The specific volume of the steam is the ratio of the mass of the steam, which does not change, and the total volume that does not change. Also, this is not changing. The steam quality changes instead, and we find 1.13 into 10 to minus 4. The mass of the vapor is the total mass into the steam quality. The mass of the water is the total mass minus the mass of the vapor. But this does not change significantly with respect to the state A. The volume of the water is the product between the specific volume of the water and the mass of the water, and the volume of the vapor is the total volume minus the volume of the water. The internal energy and the specific enthalpy we can calculate as we have seen in the previous slide, because they are only function of temperature and the steam quality. For the fluid 1, the pressure we calculate by means of the state equation. The mass does not change, the temperature we know, and the volume is the same of the volume of the vapor, and then we can determine now the total pressure as sum of the pressure of the steam and pressure of the air. We find 2.46 bar absolute, so the pressure increases. The other variables for the air are the internal energy and the specific enthalpy, which are only function of temperature. For the mixture, we can calculate the total enthalpy of the state B as sum product of the masses and the specific enthalpies in the same way as we have seen in the previous slide. All the findings are now resumed in the table, also for the state B. About the state C, the transformation BC is isobaric. We need to guess a temperature. We get the temperature from the experiment, that is 126 degrees. The volume of the vapor we assume is the total volume of the lower chamber of the moka pot,
the same volume of the state B, 375 cubic centimeter. For the steam, from the temperature, we calculate the partial pressure, 2.39 bar, the specific volume of the water, the specific volume of the vapor, and then the mass of the vapor as ratio between the total volume of the vapor and the specific volume of the vapor. Then we calculate the mass of the water as the difference between the total mass that does not change and the mass of the vapor. But also in this case we have no significant change versus the state B and also versus the state A. The volume of the water is the specific volume of the water times the mass of the water, and the total volume is the sum of the volume of the water and the volume of the vapor. We find 697 cubic centimeters. The volume of the steam is the ratio between the mass of the steam that does not change and the total volume that has changed. The steam quality is 1.65 into 10 to minus 3 and also changes. We can calculate the other variables, the internal energy and the specific enthalpy, as we have seen in the previous slides. For the air, the pressure we calculate by means of the state equation, considering that all the variables are known, and in particular the volume of the air is the same as the volume of the vapor, and the pressure of the mixture of the state C is the sum of the partial pressure of the steam and the partial pressure of the air. We find 2.64 bar. This is different from the original pressure of the state B, that was 2.46 absolute bar. Then we need to change iteratively the temperature till when the pressure of the state C equals the pressure of 2.46 bar. And the found temperature is 123 degrees. Soon after, we need to recalculate all the parameters above. For the mixture, the enthalpy of the state C is the sum product of the mass and the specific enthalpies, as we have seen in the previous slides. Hereby the table with all the parameters for the state C. The temperature is also evidenced in yellow. For the state D, we consider the isenthalpic transformation, and we know that the pressure is the atmospheric one. We guess for the temperature 99 degrees. And for the steam, we calculate the partial pressure, the specific volume of the water and the specific volume of the vapor, getting the same results as done in the slide 12, because we start from the same temperature. We guess also the volume of the vapor to be 1 into 10 to minus 2 cubic meter. The mass of the vapor is, as usual, the ratio between the volume of the vapor and its specific volume. The mass of the water is the difference between total mass of the steam and the mass of the vapor. And in this case, this value is changing slightly from the mass of the water of the previous states. The volume of the water is the specific volume of the water into the mass of the water, and the total volume, the volume of the water plus the volume of the vapor, as usual. The volume of the steam is now the ratio of the mass of the steam that does not change and the volume that we have already calculated, and the steam quality we can also calculate with the formula we have already seen in all of the previous slides. The other variables we can also calculate the specific enthalpy and the internal energy. For the air, we calculate the pressure as the difference between the total pressure, which is 1 bar absolute, and the pressure of the steam. The volume we calculate by using the state equation, and we recognize that this volume is now different
from the volume of the vapor that we have guessed above. We calculate also the other variables of the air, and of course, because we start from the same temperature, we get the same results as in the slide 12. For the mixture, we calculate the total enthalpy in the same way we have seen in the other slides, and we find 139 kJ. That is different from the enthalpy of the state C calculated in the previous slide. Also, we need to change both the guessed values of the temperature and the volume of the vapor till when the volume of the air equals the volume of the vapor and the enthalpy of the state D equals the enthalpy of the state C, because we are looking for an isenthalpic transformation. Eventually, the found values for temperature and volume of the vapor are 99.5 degrees and 2.39 into 10 to minus 2 cubic meter, which is definitely much higher than our guess. And soon after, we have to recalculate all the parameters accordingly. The found parameters for the state D are in the table aside, while the temperature and the volume of the vapor are evidenced in yellow. Now we want to see a comparison between the experiment and the simulation. What about the maximum temperature? The found temperature in the experiment is 126 degrees, while in the simulation we get 123. What about the cooking time? The heat calculated is capital Q equals total enthalpy of state C minus total enthalpy of state A. We get 130 kJ. The power of the cooking plate has been measured at slide number 6. Capital P equals 0.46 kW. The expected cooking time is then capital Q over capital P, that is 284 seconds, corresponding to 4.73 minutes versus 5.08 minutes from the experiment. There is a deviation of 7%. What about the produced coffee? The water in the upper reservoir is 272 grams. The water in the coffee funnel is 19 grams, altogether 291 grams of product. In the simulation we find the mass of the water left, as per slide 14, is 289 grams. The deviation is less than 1%. Some observations. The transformation AB is isochoric. The transformation BC is not perfectly isobaric because the pressure raises from 2.46 bar absolute to 2.64. That because we have measured 126 instead of 123 degrees. The transformation CD is isenthalpic because the pressure after the coffee extraction drops back to 1 bar absolute. The results are very sensitive to the coffee density, how much the coffee powder is pressed in the funnel, and therefore we need many experiments to confirm the trend. But what to do with all that coffee? We will see in the next slide.
This presentation had the purpose to display a possible thermodynamic model to explain the working principle of a coffee pot. While comparing the simulation with the reality, we noticed some discrepancies, but, to be honest, not so big. Therefore, we may judge the model is good. Thanks again for your attention, and see you again. Bye bye.